More threads can make a server faster, but if you add so many, your server can actually become slower. So what's happening inside the CPU? Engineers sometimes call this the context switch trap. Let's break it down. When developers first learn about concurrency, the solution feels obvious. If a server receives more requests, we just create more threads. More threads means more work happening at the same time. At least that's the intuition. But there's something important happening underneath. Even if your program creates hundreds of threads, a machine with 4 cores can still only run 4 threads at the same moment. Even if your program creates hundreds of threads, each core still executes them one by one. So when many threads are ready to run, the operating system has to constantly switch the CPU from one thread to another. That process is called context switching. The CPU runs a thread for a small time slice, often just a few milliseconds, before the scheduler switches to another thread. Then the operating system pauses it and switches to another thread, then another, then another. This rotation happens extremely fast, but every switch has a cost. So, what exactly happens during a context switch? When the CPU stops running a thread, it has to remember where the thread stopped. Things like the value in the CPU registers, the current instructions, the position of thread stack. All of this state is saved by the operating system, usually inside a structure called thread control block. Only after saving that state can the CPU load the state of next thread. So every context switch really means pause one thread, save its state, load another thread state, resume execution. And none of this work belongs to your application. It's simply the operating system managing threads. If this happens occasionally, the cost is small. But what happens if it happens thousands of times per second? Imagine a server with hundreds or even thousands of runnable threads. Each CPU core still runs only one thread at a time, so the operating system keeps rotating between them. A little time for one thread, then a switch, then another thread, then another switch. If the system keeps rotating constantly, the CPU starts spending a lot of time just switching tasks. Less time running your code, more time managing threads. And that's only the first layer of slowdown. The deeper cost appears inside the CPU's memory system. Modern CPU are fast largely because of caches. Caches are small pieces of memory that sits very close to the CPU. Instead of going to RAM every time, the CPU first checks these caches. There are several levels: L1 cache, L2 cache, L3 cache. If the data is already in the cache, the CPU can access it extremely fast. But if the data isn't there, the CPU has to go to RAM, and the RAM is much slower. So the caches work best when the same thread keeps running for a while because its data stays nearby. But thread switching breaks that pattern. When the CPU switches from one thread to another, the new thread usually needs completely different data. But the cache still contains the data from the previous thread. So the CPU has to load new data again. This leads to cache misses. The CPU now has to fetch the data from the deeper cache levels or even from the RAM. So thread switching doesn't just cut scheduler time, it also wipes out useful cache state. The CPU keeps rebuilding that state again and again, and that slows things down even further. But there's another problem that appears on multi-core system. CPU don't cache individual variables. Instead, they cache blocks of memory called cache lines, usually about 64 bytes. Now imagine two threads running on two different CPU cores. Each thread updates a different variable, but those variables happen to sit inside same cache line. Even though the threads are touching different data, the CPU treats that cache line as shared. So the cache line keeps moving between the cores. One core updates it, another core invalidates it, then it moves again, over and over again. This is called false sharing, and it creates a lot of extra memory traffic between CPU cores, which slows down the system. Because of this, engineers try to design data structures carefully. Sometimes they separate frequently updated variables so they do not share the same cache line. This avoids unnecessary cache invalidations between CPU cores. Now we can connect all of this back to server design. If a server creates too many runnable threads, several things start happening at the same time. The operating system performs frequent context switches. The CPU time is spent saving and restoring this thread state. Caches consistently lose useful data and have to rebuild it. And memory traffic increases between CPU cores. Instead of improving performance, the system becomes less efficient. The server spends more time managing threads than actually doing any useful work. This is why modern server architectures avoid creating unlimited threads. Instead, they use more controlled designs, such as thread pool limit in the number of active threads, event loop avoid blocking threads while waiting for I/O, and worker processes handle CPU heavy tasks separately. The goal is simple: keep the CPU doing useful work and avoid unnecessary thread switching. Understanding this hidden cost is part of thinking like system engineer, layer by layer.